Alright, so today we're going to talk about accuracy, precision, and percent error. So by the end of this, you can collect data with accuracy and precision, and then you can compare the terms accuracy, precision, how these terms, as well as percent error, illustrate the importance of repeatability in a laboratory investigation. So, accuracy and precision. Accuracy refers to the closeness of measurements to the correct or accepted value of the quantity measured, while precision refers to the closeness of a set of numbers or measurements of the same quantity made in the same way. So, if I had, oh, you can't see that, 1, 2, 3, 4, that would be accurate and precise, right? I've hit the center of the bullseye and they're all close together. If I had something like this would be precise, they're all close together, and not accurate because we haven't hit the center of the bullseye. And then if I did something like this, it would be neither accurate or precise because I've not hit the center of the bullseye and that's just all over the place. There are two different types of errors. So there's an indefinite, random, or repeatability error, and this is where a measurement has an equal probability of being high or low. So our third target would have an indeterminate or random error. If we have a systemic or determinate error, it occurs in the same direction each time, either always high or always low. So our second target would have a determinate error. So let's look at some practice problems. So target 1, I'm going to give you guys a second, pause the video here, answer these questions on your own. So target 1, we can see that it is not accurate, right? We have not hit that bullseye, but it is precise. We've grouped those things pretty closely. So is that systemic error? Are we going in the same direction each time? We are. And then is that a reproducibility error or random error? Is it all over the place? It's not. Target 2, is it accurate? Yes, it's accurate, right? We've hit the center of that bullseye all 5 times. Is it precise? I would say it is. We've gotten pretty close. Does it have any systemic error? Not really. I could see you arguing that this one right here is systemic. Does it have a reproducibility error? Did they not reproduce the same measurement every single time? No, I don't think there is much error there. And this last one, is it accurate? Yes, I've hit the target once. Is it precise? No, I have not grouped them together. Does it have systemic errors that going the same direction each time? It's not. Does it have a reproducibility error or is it random? It is. Then, if we look at these sets of data, we're moving on to question 2. So students were tasked with measuring the mass of a paperclip in preparation for a density assignment. The following data are the measurements each group collected for the paperclip. The known mass is 1.04. So I want to give you guys a second to look at this and decide if they're either accurate, precise, or both, or neither. All right, so group 1, we have trial 1 at 1.01, trial 2 at 1.03, and trial 3 at 0.9. So would you consider this accurate, precise, or both? I would say it is pretty close to both. Right? They're all pretty close together. And they're all relatively close to 1.04 grams. Now, group 2, trial 1 was 3.86, trial 2 is 3.80, and trial 3 is 3.83. I would say that these are precise, but they're not accurate. I'm going to just leave a P there. And that they're close together, but they are nowhere close to 1.04. Group 3, I have a 10.13, a 10.13, and a 10.13. Is that measurement accurate, precise, or both? Now, once again, I would say this is precise, right? They've all gotten the exact same value across the 3 trials. It is significantly higher than 1.4 grams. And then finally, group 4, trial 1 is 2.05, trial 2 is 0.23, and trial 3 is 0.75. Is that accurate, precise, or both, or neither? Well, I would consider that neither, right? It's not precise, they're not all close together, and it's not accurate. None of those numbers are very close to 1.04. All right, so now that we've talked about what precision and accuracy are, we're going to move over to talking about what percent error is. Percent error is calculated by subtracting the accepted value, so what you expected to get or what you should have gotten, from the experimental value, the thing that you got during the lab, dividing the difference by the accepted value and multiplying it by 100. Percent error has a positive value if the accepted value is greater than the experimental value, or it has a negative value if the accepted value is less than the experimental value. You can put them in absolute value. I don't care if it's percent or positive or negative. It does not matter to me. You can leave it as positive, negative. You can put them in percent. You can just drop the positive or negative. It means the same thing. It is also very common to simply just take the absolute value of the percent error to always obtain a positive error or a positive value of the percent. Right? Like I said, you can just drop the negative sign when you answer the question. It's not going to bug me. All right, so let's look at some practice problems for percent error. So a student estimated the mass to be 250 grams. Upon carefully measuring, it was found the actual mass was, or to be, 240 grams. What was the percent error? So if we remember our equation, right? Minus accepted all over times 100. So that is my equation. Now let's plug in our numbers. So our experimental would be our estimated, so 250 grams. Our accepted would be the actual, right? So the actual mass, 240 grams. All right, so we grab our calculator, right, and we plug it in. 250 minus 240, right, divided by 240, 124. and then I multiply that by 100. Okay. Give me a second. I don't want to convert to decimals. Right? So my answer would be 4.17. When I have answered a question, I box it and I move on. So our next practice problem is an experimental measurement of 10.4 milliliters was taken, and the actual measurement was found to be 9.7. What is the percent error? So the first thing we do is we're going to write our equation. I'm going to simplify it so I don't have to write it all over again. E minus A over A times 100. And I'm going to plug in my two values, right? My experimental measurement was 10.4 minus my actual measurement, which is 9.7, all over my actual times 100. Now that I have my equation, we're going to plug it into the calculator. Whoops, sorry. So I got 7.21. Sorry, 2, because I round up with a 6. Write my answer down, and I box it. All right, let's look at some more practice problems. All right, so Sarah's bottle contains 144 milliliters of soda. According to the label, she measures the soda in a graduated cylinder and she records the volume to be 152 milliliters. What is the percent error? So these are my two numbers. I'm going to write down my equation. Right, and I'm going to plug it in. So this is the accepted. This is the experimental. Minus, make that look better. There you go. Minus, wow, I'm struggling with writing numbers today. 144. So if I plug this into the calculator, all right, (152) minus 144 divided by 144 times 100. Oops, I did that wrong. Lineal number, convert to decimal. So I got 5.56. So I write my answer. Box it, and I move on. Right, so in your note packet, you've got 4 more. I'm going to let you guys do these on your own, and we'll come back and look at them together.